Kruskal's algorithm is also designed using the partition property. If we have a partition of our graph that must be connected, we can choose whichever edge connecting them is minimal in order to build a minimum spanning tree. So Kruskal's algorithm begins with initially a cloud around each vertex, and it uses a priority queue of edges to repeatedly find the next edge, which is with the smallest edge weight. Now, as long as this edge is necessary in the minimum spanning tree, meaning that it will connect two parts of the graph that were not previously connected, then it'll use this edge. If, however, the endpoints of the edge are already connected, then that edge isn't necessary. Now, in order to check if two vertices are connected, we check if they belong to the same cloud. Now here, each cloud represents a set of vertices which are connected to all other vertices belonging to the same cloud. So in effect, we maintain each cloud as a minimum spanning tree of just the vertices in that cloud. In order to form a minimum spanning tree of the entire graph, we must join together each of these smaller clouds. So what is the total runtime of this? Well, it depends. We know we can add all edges to a priority queue in total big O of m time, since we've got m edges, using bottom-up heap construction. And we know that this while loop, in the worst case, may go through and have to evaluate every edge of the graph. So it might iterate m times. And inside this while loop, remove min costs, remove min costs, just one call to remove min costs log m. Since we might call this m times, this is big O of m log m. But what's not really clear yet is how we can efficiently implement these operations of finding for a vertex what cloud it belongs to, and also how to merge clouds together. So we'll see how to do that in a moment, but keep in mind here the difference between Prim's algorithm and Kruskal's algorithm. Both of them are using this partition property to form a minimum spanning tree by using an edge of minimum weight. Prim's algorithm does so by starting at some vertex and kind of building its way out from that starting vertex, adding edges in some other, maybe connected to some other vertex, but at least building one entire spanning tree from that starting point and then adding vertices. Prim's algorithm maintains a priority queue of vertices, which represent vertices outside the cloud that we have a distance label that we're going to take whichever one is smallest and add it to the cloud. Kruskal's algorithm maintains a priority queue of edges. So edges are ordered by their edge weight. We take whichever edge has the smallest edge weight, where that edge could be anywhere in the tree, and add it as long as it's connecting vertices of different clouds. So the difference here is maintaining one cloud initially around each vertex. With Kruskal's algorithm, it will decrease the number of clouds while increasing how many items are in that cloud, whereas with Prim's algorithm, this was just one cloud that we expand upon. Okay, so how do we implement these different clouds? Well, essentially what we're maintaining is a forest of trees. So each cloud represents a minimum spanning tree that we're constructing of the vertices belonging to that cloud. And we only want to accept a given edge if it connects distinct trees, if it belongs to different clouds. So we need some kind of a data structure that maintains a partition, a collection of disjoint sets that supports finding which cloud a vertex belongs to, so what set does this vertex U belong to, and joining two clouds together when we choose to add this edge which connects different trees. So how we can replace the set which stores U and V with the union of those two sets. Well, we can accomplish this by having a cloud object which references a sequence of all of the vertices that belongs to that cloud, with the additional stipulation that each vertex in the sequence also has a pointer back to the original cloud object that it belongs to. So given this vertex, we can immediately determine in constant time, oh, this belongs to cloud A. This one also belongs to cloud A. So given a vertex, we can find the cloud it belongs to in constant time, just by following that reference back. And if we have vertices that belong to separate clouds, say we have here cloud B, which contains vertices, let's just say this is X and Y, and each of them have a pointer back to, both of them belong to cloud B. If we find that here is, or let's call this one V. Here is vertex U and here's vertex V. They belong to different clouds. Now we want to merge these two clouds together. We can do this by taking whichever one of these sets is smaller and appending it to the end of the larger set. So in this case, we would just add X, Y, and V to the end of A. So we'd have here X, Y, V, and we would update their references to, instead of going back to B, they would go back to A. Now why we take the smaller one is because this dictates how many changes we'll have to make to this larger set. So in this case, we only had to, the cost of this merge operation was linear in size with respect to the smaller set. So note that whenever we merge two clouds together, the size of the resulting cloud is at least double the size of the smaller cloud. So the number of times that we would need to merge clouds together until we obtain one cloud containing all vertices is log n. This is the number of times we would have to, beginning with one vertex, repeatedly double until we have n. So the total cost to merge is big O of n, and the merge happens at most big O log n times. So the total cost for merging operations is big O n log n. All right, so let's go back to Kruskal's implementation of finding a minimum spanning tree now. So we have a partition of vertices in order to maintain all clouds, initially one cloud around each vertex. We have a priority queue of edges, so they're sorted by their edge weights. So we've got m elements in this priority queue, and an initially empty tree T. This will be our minimum spanning tree when we're finished. And we'll go through every edge in the priority queue by ascending weight. So we'll remove whichever element is smallest. So how often do we have to do this? Checking to see if Q is not empty. This will cost total m. We'll make m calls to remove the minimum element. So the total cost of all the times we're going to call this line is m log m. Finding if two vertices belong to the same cloud or not. Just one check to this is constant time, since we're going to call this at most m times. That's total is m. And then sometimes we add an edge to this minimum spanning tree T. So we know that the number of edges that we're going to add actually is n minus 1. So let me just put up, just roughly here, this is n, but exactly n minus 1 edges to our minimum spanning tree. And for each edge added, we perform this union operation, which we saw in the previous slide is n log n. Okay, so our total cost here is just the summation of these operations. So we're left with big O of m plus, we have m log m, and we also have n log n. All right, so let's simplify this. One, we have m and we have m log m, so this is a faster growing function. So when we simplify this, we can get rid of this slower growing function. Now between m log m and n log n, how do we combine this? Well, it's important to note that log m, because m is big O of n squared, this is big O of log n squared. And from rules of logarithms, log of some, let's say log of x to any power is that power times log x. So we have this is big O of 2. This is exactly equal to 2 log n, which means it's equal to big O log n. Okay, so we could express this now as here m log n plus n log n. So at least those logarithmic terms are the same. And we're left with n plus m, all of that times log n. And again, if we're working with a connected graph, since n is big O of m, then we can express this just simply as m log n as well. Let's see an example of this now. So we have this is our initial graph. Kruskal's algorithm initializes a cloud around each vertex initially, and will process edges in ascending edge weight. So we've got the first edge to consider is this edge 144. Because it connects two vertices that belong to different clouds, we will include that vertex and then join their cloud. So this is a new cloud containing both vertices. Now we look at the next smallest edge weight, which is this 184. These vertices belong to different clouds, so we include the edge and we merge the clouds. The next smallest edge weight is 187. Again, it connects vertices belonging to different clouds, so we add the edge and merge clouds. The next smallest edge is 337, so this doesn't have to be connected to this larger cloud. So we'll add this edge and connect those clouds. And the next smallest edge, let's see, it looks like that'll be 621. Because these vertices belong to different clouds, we add it and merge clouds. And then we'll process, let's see, it looks like the edge 802 is the next smallest one. Oh, no, 740 is the next smallest edge. But we've already connected the vertices ORD and JFK, and we know this because they belong to the same cloud already. So even though we're going to process this edge next, we will not include it. So now we'll move on. Now the next smallest edge is 802, and this connects vertices which weren't already connected, so we add it and we merge their clouds. And the next smallest edge is 849, but those vertices belong to the same cloud, so we don't use it. Same thing for this edge 867, so processing edges again in ascending order here by edge weight. And the next one that we're going to look at is this edge 946, which connected two vertices that weren't connected already. Then the edge 1090, because those vertices were already connected, then we don't include that edge. And then, let's see, the edge 1121, again, since these vertices belong to the same cloud, they were already connected, we don't include that edge. And then the next smallest edge here is 1235. So because LAX and DFW belong to different clouds, then we will include this edge. And now we already have a cloud which includes all vertices, so any remaining edge that we had will not be included.